Welcome, Math 105, to our second act of the course. So we've just come through the first exam this semester, and what that means for us in principle is that we've turned a corner. So the whole first unit of our course this semester was spent really talking about questions of sets and logic. So how do we think and reason mathematically using sets to collect groups of elements together, and then using logical reasoning to be able to parse the logical content of an argument to see whether or not the argument's form is valid. So that's the kind of reasoning that I think people don't always recognize as being particularly mathematical. It's sometimes philosophical, sometimes logical. What makes it mathematical is that really all of mathematics rests upon this foundation of logic. Everything we do, everything we deduce mathematically is deduced through a logical process. Whether that logical process is just about concepts like sets and ideas, or whether it's about numbers, or whether it's about statistics, there's a logical, analytical underpinning of mathematics that characterizes math as math. And so what we're going to do next in our second phase of the course is we're going to turn our attention back to what is sort of more traditionally probably understood as mathematics. It's the kind of mathematics that you're probably accustomed to having done in middle school and high school. But when we do that, I want to look at algebra, essentially, introductory basic algebra, as we're going to work through for the next 4 weeks or so. I want to look at it through the lens of why should we know this stuff? How does algebra equip us with tools to actually reason mathematically about the world around us and answer questions that we might actually care about? In particular, the biggest step in this process is that step by which we access familiar forms of mathematical reasoning, which are almost completely based on manipulating formulas and variables and solving equations and everything that you remember high school algebra class being about. How do we access those forms of mathematical reasoning, which are abstract and which you don't tend to see on the front pages of the New York Times? How do we access those forms of reasoning from the contexts of our everyday lives, our professional lives, our public discourse, our personal finances? Where does that stuff actually help us to be more successful in our careers, in our education, and in the world around us? Those are really the questions I want us to think about as we go forward. So this second act of our course evolves in sort of 3 steps. The first one that we're going to work through this week is just to sort of plug ourselves back into the most basic algebraic formula-based manipulation that we learned in Algebra 1, but to do so thinking more expansively about how to communicate mathematically. So one of the big takeaways I hope from today is that we can express the same mathematical thought in any of sort of 4 different ways. And I may have talked about this a little bit already, but one way is using the traditional formulas that you remember from high school, or maybe don't remember. Another is to express a thought using words. We talked a lot about this one actually during the sets and logic unit. If you can express a mathematical thought using words, that doesn't make it any less mathematical. And so the verbal form of expression, it's how we communicate, it's how mathematicians communicate. The third form is using a visual representation. And in this unit, when we're starting to talk about algebra and function models, the graph as a graph is going to be one of our more important tools that we use for communicating an idea about algebra. And then finally is a set of numbers that take the form of a table of data. Having a table of data is very often where a mathematical problem is unearthed in the real world or in the business world or whatever, right? That if we can go measure something and collect a set of observational data on it, that really should give us a toehold into doing something mathematical to describe that observation. So we're going to talk about those 4 different ways in which we can express mathematical thought and how to convert back and forth, how to be conversant in all 4 of those languages. For me, that's one of the big objectives of this course, is that you're not only able to express a mathematical thought using a formula, but that you're also able to translate that formula into a good verbal description, translate that verbal description into a graph, write down a graph that represents a table of data, and then what we're going to focus on a lot today, take a table of data actually for the next 3 weeks, take a table of data, and through an iterative process of going back and forth between the different ways of communicating and understanding that data, eventually get down to an algebraic formula that we can use to model that data. That's ultimately what we do from here until the end of this unit, is a process of figuring out how to unearth a formula and then use that formula that's suggested by a set of data. That's a very long story, and we're only going to get a chance to scratch the surface in this semester. But if you're interested in more of how this stuff works, a course in applied mathematics or mathematical modeling, or sometimes courses that go by names like quantitative analysis, quantitative methods, if those are often used in the business world, those are the kinds of courses that tend to treat ideas like these in a lot more depth and a lot more rigor than we will. But what I'm hoping is that we will have a good enough taste of the material in the next 3 or 4 weeks that you'll feel equipped to be able to do something with the data that you get from the world around you. So that's the goal over the course of the next 3 weeks. If you're currently enrolled in my class and you're watching us live, welcome. If you have questions about what we're talking about live during the session today, feel free to drop those into our Slack channel under Doctor's Office. If you're not a part of our course this semester, but you're watching us live via Twitch, feel free to contribute any questions that you might have into the Twitch chat. And again, if you're watching this video after the fact via YouTube, don't forget that there will be timestamps on the video description underneath me, and you can use those timestamps, click on them to jump to different places in the video so that you can find what you're looking for. So first of all, let's start talking about the 4 different forms of expression that we can use to express a mathematical idea. And to get us started thinking about this, what I want to do is actually start with a table of data. So a table of data is the sort of prototypical way of thinking about what a numerical way of communicating a mathematical idea looks like. And this particular table of data is drawn from a public survey that is actually part of a Newton Alta resource for this course. So here's the nature of the data. What the data is going to communicate to us is it's going to sort of tell us about the number of associate's degrees. So these are degrees typically awarded by community colleges that were awarded in the United States over time. So in 1981, there was a certain number of degrees awarded. In 2014, there was a certain number of degrees awarded, and a bunch of other years in between. Right? So this description that we're seeing right here is what we would call a numerical description. This is the kind of data that does appear in public communications about mathematics. Whether those public communications are magazine or newspaper articles, or sometimes little pieces on the news when you're watching on TV, all the way up through more skilled publications, things like trade publications and white papers that might be produced by businesses or nonprofits. Data is big business, and it's never been bigger than it is in our modern world today. There is so much data in our society, and data drives so many of the decisions that we make and so many of the ways that we interact with one another and with the world. More now than ever, because we have the capacity technologically to store and to analyze ever-growing amounts of data at the same time. And the amount of data that's been collected even about you and is being stored by various governmental and private companies that are out there is just staggering. Our last act in the course is going to be to really get a surface view about statistical reasoning and what are some of the statistical elements that can help us to understand trends from very large sets of data. So big data is big business right now, and so the numerical way of expressing a mathematical thought is where a lot of good mathematics and inference, and also a lot of bad mathematics and misleading inferences begin. So it makes sense that using numbers to represent what we're talking about is sort of a base level of how we get access into the mathematics that we want to do. So this would be a table of data for this. The problem that I want to tackle here that's going to motivate our different ways of communicating, the problem is, how do we draw some sort of an inference or make a decision or have some sort of conclusion that's based on the data that we're seeing here? So ultimately, to put a finer point on it, the question that I want us to answer is, based on the data that we're seeing in this data table, how many associate's degrees would we predict will be awarded in the year 2020? So one of the powerful things that having a mathematical model is going to do is it's going to let us make an informed prediction about the future. Or about a data point that we can't see from the data that we were originally given. Having a model, particularly a model in terms of a formula, is going to let us make informed predictions and extend what we already know from historical patterns into looking forward into the future and saying, what do we think is going to happen? That's probably the most valuable thing that we can do if we do it wisely from a good mathematical model of a set of data. So that numerical form of expression is sort of way number one that we're going to think of being used to communicate mathematical thoughts. So let me real quickly sort of make a little illustration here. So in our 4 different modes of mathematical communication, the first one that we've talked about here is the numerical. So communicate with numbers, which again very often takes the form of a data table. So let me paste the data table that we just looked at into this screen. Now it bears mention at this point that a data table with just numbers in it is not going to be a very useful aid if somebody just looks at this list of numbers in the newspaper or something. Numbers without context are what I like to call decimals without a point. If we want to really understand how to integrate these forms of mathematical reasoning with our everyday life, we need to make sure that we take care to provide context to anything that we present to a reader. So I can't just put this list of numbers out there and expect that people are going to understand what this list of numbers is actually telling me. So at the very least, what I want to do is remind anyone who's looking at this what these various quantities in these rows here represent. So this number in my second column, remember in the introduction to this data, sort of described that the number in the Y column here is the number of associate's degrees awarded, and it's being measured in thousands. So this 410 that's sitting right here is not 410 associate's degrees, it's 410,000 associate degrees that were awarded in the United States. So we definitely want to make sure that we're presenting that information in our table. So number of degrees in thousands. So provide a meaning and provide a unit of measurement anytime you're introducing a measured quantity, so that if I look at one of the numbers in this table, I know what that number means. 569,000 associate's degrees awarded. And then the same thing for our other variable, which in this case we're calling x. This x is the year. And so this 569,000 associate's degrees were awarded in the year 2000. So a data table is not only giving us a bucket of numbers, it's also setting up a relationship between the numbers in one of the columns and the numbers in the other column. So this table is sort of expressing a relationship between what year it was, so the values of x, and the number of associate's degrees that were awarded in that year. Those are the corresponding y values that are over here in the other column. And so what we're really setting up here is we're setting up a relationship. And because we're setting up a relationship, I'm going to actually add that into the beginnings of what is going to eventually become a verbal description. The number of associate's degrees awarded in the U.S. So here we're going to write out a sentence. Was related. In other words, sort of varied from year to year. Right? So I'm going to write that observation down. That's a sentence that helps, at least initially, for us to make some sense of what this data table is telling me. There was some relationship between what year it was and how many associate's degrees were awarded in that year. We're, of course, going to make that verbal description much more specific and pointed as we go along. So that's sort of what we get for now at least, out of a numerical description of a relationship between two measured quantities. So the next place we want to go is to think about a graphical form of communication. Graphical forms of communication are one of the most powerful ways to communicate a mathematical thought. And we've already seen in our semester a number of different graphical tools that we can use to understand mathematical reasoning. In particular, the Venn diagram and the Euler diagram. Those were two of our main sort of graphical tools that we've used in our course up until this point to communicate these mathematical ideas. Not only can we use them to communicate, but because they communicate to us so well, visual representations can also be helpful computational and analytical tools. They help us not just to communicate, but to solve problems. What's the old adage? A picture is worth 1,000 words. There's definitely a grain of truth to that. My own self, I do feel like if I have a picture for something, it really helps me to understand that something to a greater degree. So I rely on graphical interpretation and graphical presentation a lot. In my teaching, yes, but also in my research and in my learning, everything else that I do as well. I kind of have that preference for having information presented to me visually. Not that I don't also learn in other ways, but I really find that multiplier effect of a picture being worth 1,000 words really helps me to learn and understand. So let's see if we can come up with ways of depicting a relationship between two measured quantities in a graphical way. So the standard trope, of course, for depicting a set of data, the way that you had to do over and over and over again in your algebra classes in high school, was to use what's called a Cartesian coordinate graph. So a graph using Cartesian coordinates. Sorry, that's a telemarketer ringing my phone. So a graph using Cartesian coordinates. What does this mean? This is the familiar trope that you're used to from high school algebra, where on my two-dimensional page here, I have a horizontal direction, and I assign to that horizontal direction one of my two measured quantities, usually the independent variable, whatever that means, usually the variable that we label as x if we have no other reason to prefer a different letter over x. And so in this case, that would represent the year. And then a vertical direction that we assign to the other measured quantity, in this case y, the number of degrees awarded in thousands. And then the usual strategy, right, is that we take each one of the observations that came from our data table and we represent that observation as one point on this Cartesian coordinate system. For example, this point, in the year 2000, there were 569,000 associate degrees that were awarded. We depict that by finding on the x-axis, so this line that we drew horizontally right here that proceeds from left to right on my page, we think of that left to right axis as being like a number line. And on that number line somewhere is the number 2000. Same thing with the vertical axis, the y-axis in this case. We think of that as being a number line in and of itself as well. And somewhere along that number line is the number 569. And once we've located those two places on our number line, all we then do to finish our communication is we look for the point in the rectangular coordinate system that is on the same horizontal level as the number 2000 and is at the same vertical location on my page as the number 569, and we place a point right there. And we label the coordinates of that point. So when we say coordinates, we mean a list, an ordered pair of two numbers, with the horizontal coordinate coming first and the vertical coordinate coming second, that describe the location of that point inside of my coordinate system. So the usual trope for how we represent this relationship is we just do that process. For each of my observations, we make each of these observations one of the points, ordered pairs in Cartesian coordinates, that we place on our XY graph paper, if you like. And if we do that same thing for all of the points that are a part of our comparison over here. So in addition to 2,569, I also want to put some other points like 2010, 719 rather, sorry. So 2010 is going to be over here. It's going to be to the right of 2000 because it's a greater number. Same thing with 719. 719 is going to be somewhere above 569. And so at the end of the day, we're going to look for the place where those two intersect, where those two meet. We'll put another point there. And so on, right? Eventually, we'll get a picture, we hope, that emerges. If we place all of our known points onto a graph, then we should be able to tell, at least sort of roughly, we should be able to tell some story about the relationship that we described here in words. One of the best ways to do this is probably not with a pencil and paper. One of the ways that we want to get accustomed to doing is using technology. In particular, as we go into next week and the week after, technology is going to be an essential tool for us in understanding how to get a story out of a large set of data. So we won't probably need technology this week. I'm going to use it in this live stream to get us some exposure to it. But starting from next week, you're going to want to have access to a piece of technology that can do this kind of analysis. There are sort of two tools that I recommend. The one I'm going to show you today is a free online graphing calculator tool called Desmos. This is great. This really does replace the $150 graphing calculators that you used in high school and never are going to use again, most likely. It's a great free online tool. It works well as a mobile app as well. So that's the one I'm going to show you today. But also a more powerful and flexible tool that's in use in more workplaces in the United States is Microsoft Excel, so spreadsheet software. We're going to look next week when we start doing that kind of analysis. We're going to see it done using the free online Desmos tool. We're also going to see it done using Excel. And at the end of the day, I don't care which one you use, but I do hope that you'll come out of our course with some experience using one of those tools or the other, because that's a really valuable tool going forward into any career that you might go into when you graduate. So let's take a look at the free online tool called Desmos. So how do you access it? Just go to desmos.com. You can sign up for a free account if you want to, or you can just click the button that says Start Graphing, and it'll give you the graphing calculator right away. So that's the tool into which I've placed this set of data. I've also arranged my coordinate system here so that my x-axis is going from 0 to 500 to 1,000 to 1,500 to 2,000 over here on that side. You can adjust your range in Desmos using this little wrench button up here. So if I want my x-axis to go from the year 0 to the year 2020, I can type that in. With my y-axis, number of thousands of degrees awarded, maybe I want that to go from 0 to 1,200 thousands of degrees awarded. So this way I know I'm seeing as much of the XY coordinate system as I want to see. And then I'm just going to have Desmos plot all of the ordered pairs from my data set in this graph, which it just did. The problem is this isn't a terrifically useful picture right now, because my x-axis, my number of years, is extending from the year 2000, or really 2020, all the way back to kind of the dawn of the modern era, right? The year 0, the year 0 common era, right? That is way too many years to really get a valuable picture out of the data set that we use here. So one of the things that I want you to be empowered to do is to choose in your visual representation, in your graph, what is an appropriate range of the x-axis and the y-axis to see, on the one hand, or the more sort of common way of understanding how to do this, because these numbers, 1981, 1990, 2005, 2014, those are also big numbers. And so when it comes time to actually do calculations with these numbers, it might be helpful to make those numbers smaller if we can. So here's a common way in which that's often done. Instead of using the x variable here to represent the year itself, what's very often done is we'll use x to represent the number of years since 1980, for example, right? So rather than using 1981 to represent the year 1981, we can just make this the number 1. 1 year since 1980. Then 1985 would become 5. 1990 would become 10. 1995 is 15. 2000 would become 20. years since 1980, 21 years since 1980, 25, 30 years since 1980, 34 years since 1980. And the benefit for this is now if I go back in and I set my ranges again, now the x's, the numbers that I care about in my x-axis column, maybe I can just do those from 0 to 40 or something. And that really helps to space out the data points so that we can more easily see what the trend is that might be evident. So now that I've done that rescaling, and I'm going to change my axis title here to say years since 1980. Now I have what I think to be a lot more valuable picture of the trend that's kind of emerging here. So let me take a moment and grab that picture, and we'll put it back onto our other screen so that we can use this as our first sort of graphical representation of what's being told in the numerical story. One of the things about graphical representations is because they're so powerful, they can communicate a lot of information in a small space. But for that same reason, it's also very easy to develop a graphical picture that's misleading in some ways. In fact, one of the things you learn about the visual display of information is that every graph, every picture that we can draw, does a good job at exposing some pieces of information at the same time that it does a poor job of exposing other pieces. So every graph is an incomplete representation of what it purports to represent. So all graphs have limitations in one way or another, and so it's about a choice of whether or not our particular representation has the limitations that we're okay with, basically. So here is a graph that depicts the data that came from this data table. So now that we're looking at this graph, we can actually say a little bit more about our verbal description. That the nature of the relationship between the year and the number of associate's degrees that were awarded in that year appears to be one in which, as the years go by, so as we go from left to right on the graph, as the years go by, the number of associate's degrees appear to be increasing. So as we go from left to right on this graph, the vertical locations of my points go from bottom to top, go from lower to higher, right? That generally, if we were doodling on this in a business meeting or something, we might do something like this and draw it in a circle and say, oh, hey, there's an upward trend. That's something, of course, we could have just seen by looking at the numbers in this table as they increase as we go from top to bottom. But the graphical representation is actually even more illuminating because it kind of shows us that there's maybe a difference in how rapidly these numbers were increasing back in the 1980s and 1990s, which is over here, compared to the 2000s and the 2010s, when suddenly there's this huge acceleration that happens here toward the end. So let's make that part of a verbal observation. So let's write that story as part of our verbal description over here. The number of degrees increased over the years. And especially rapidly since 2010. So on my graph, 2010, that's 30 years since 1980, right? So 2010 is right here. And that seems to be the year in which some things changed, right? After 2010, suddenly we're going up really quickly. So I'm just, as we're going along, kind of adding more observations to our verbal description of how what this trend is actually doing. Okay, so where we're ultimately trying to get to in this problem, remember, the question that I posed to you at the outset was how many bachelor's degrees are going to be awarded in the year 2020? So what that means, if we zoom out on this graph just a little bit here, what we'd be asking is if we look at the year 2020, which would be x equals 40, that would be 40 years after 1980, right? So if x were equal to 40, what would the value of y be? How many degrees would there be awarded in the year 2020? So we're going to have the ability to place a point here, somewhere along the vertical line where x is equal to 40. This is the year 2020. So the question is, how many degrees are we going to have awarded in that year? Would 1,240 be a reasonable observation, a reasonable guess? Would 946 be reasonable? Would 1,710 be reasonable? The fact is that without doing any more calculation or analysis, we're not really sure which of these predictions is really better than any other. One of the things that we might argue, for example, is that when you look at the trend in the data that was all the way up until 2010, so 2010 is right here, it looks like the increase in the number of associate's degrees was relatively steady year over year. And this 2010 number, or 2014 number rather, this 2014 number seems to be a break in the pre-existing pattern. Right? Something happened between 2010 and 2014 that was different than what had been happening up until 2010. So if we, for example, were to just throw away this 2014 observation, just ignore this point up here, then it seems like our prediction should probably be somewhere closer to here. If we just sort of follow this sort of straight line out until 2020, then 874 seems like a reasonable prediction, right? Graphical prediction. But on the other hand, maybe this rapid change since 2010 means something. And if this rapid change since 2010 means something, then probably I need to place this prediction in a much different spot. Like if I just go back to 2010 and say 2010 to 2014 to 2020 and ignore all these other points that came before it, then it seems like 1400 is a better prediction of how many degrees that we should expect to be awarded. So clearly, the hard question here is what information do we take into account to make this prediction, and how do we do it? So how I want to do that, actually, is ultimately come up with a formula. And that's going to be our main objective for today, is how do we come up with a formula to represent as simple as possible, and yet still have some power to be able to make predictions, the trend that's evident in a relationship between two measured quantities. How's that going to work? So let's talk about the formula form of communication. An algebraic formula is the mode of mathematical communication that is most particular to mathematicians and scientists. Right? Outside of mathematicians and either social or physical scientists, there aren't many people in their day-to-day lives using formulas to communicate mathematical ideas. And yet, if you think back to your experience in high school math class, formulas are probably most of what you remember. Simplifying expressions, solving equations, x's are floating around. And it's that point at which variables like x show up in people's mathematical lives that tends to be a pivot point in people's mathematical journeys. That if you got through the introduction of the variable x in your mathematical life well, like if you got that initial step into pre-algebra, if that step happened and you found yourself on firm footing, chances are that conceptual shift that you had to make helped you so much during your high school years that you probably did really well in your high school math classes. But if you stumble over that first appearance of the letter X in your mathematical life, chances are that tended to haunt you throughout the rest of your mathematical studies in high school. If you're watching this, you might be in one of those groups or the other. And so formula, because it's abstruse, because it's only mathematicians and scientists that really use formula as a primary method of tool and analysis. That means that if you're not a mathematician or a scientist walking around in the world, and most of you watching today are not, that means that using formula and becoming conversant with formula is a skill that you have to go out of your way to practice in order to improve on it. And your math class is probably the most obvious place for you to practice this mode of communication. So let's think about how we could use a formula to express the trend that's evident in the data in this data table. So the first thing that we notice is that our two measured quantities, x and y, those are going to be the variables that my formula relates together. I'll try and color code them here. So x, this is the number of years since 1980. And y is going to be a variable that stands in for the number of degrees awarded in thousands. And what I'd like to do today is for us to come up with an equation. And we want this equation to describe as best as a simple equation can, to describe the relationship between x and y that's being suggested by this data and by this graph, right? So this is ultimately where we're trying to get to. And an equation is going to be something that contains on the left side an algebraic expression. So some combination of the variables x and y together with other numbers knit together with the operations of arithmetic on those numbers. Addition, subtraction, multiplication, division, exponents if we need them, radicals if we need them, logarithms if we need them, whatever arithmetic is needed to make an algebraic expression. We'll have one expression on the left side of this equation, another one on the right side of this equation, and the equal sign in between them indicating that the values of those two expressions are always equal. Any x and y that I put into this equation needs to give me the same value on the left side of the equal sign as we have on the right side of the equal sign. And that's how an equation represents a relationship between measured quantities, is it gives us a testable criterion for whether a given x and a given y are related. That criterion is a logical proposition. Either a given x and y satisfy this equation, and so the proposition is true, or that given x and y don't satisfy this equation, so the proposition is false. When I say that the logical underpinnings of mathematics are logic, that's the reason, right? An equation is a logical proposition. It's either a true thing or it's a false thing, once we supply x and y with values. All right, so how are we going to get there? Well, let's get there by using the graph as our touchstone, right? What I'm going to do with the graph is first make a decision about how can I draw sort of a very simple curve through these points that is going to capture as much as possible the trend in this data that's being evident. We've made the observation verbally down here that the number of degrees was increasing over the years, and that especially took a turn in the year 2010. This 2014 data point right up here seems to be the odd one out, right? It's not reflecting the same trend that the first set of data points leading up until 2010 was representing. So what we might do is we might decide that let's just forget for the moment about this point that's up here. In statistics, we might give this point a name like an outlier. When you hear the word outlier, that's usually what we're talking about. That it's an observation that doesn't fit in with the general trend of the others. So for now, I'm just going to kind of ignore it. It's just one point in our data set that has a total of 9 points in it. So if we throw it away, we're probably still going to get most of what we were looking for. And so with my other points, what I'm going to do is I'm just going to kind of draw a line. I'm going to eyeball a line drawn as best as I can through all these various points. Right? This line that I just sort of eyeballed in here can be called a fit line. Right? It's a line that, as best as we can manage, passes through as many of these data points as we can and captures as best we can with a single line the trend that's evident in this data. Now, of course, my fit line and your fit line might look different. I might eyeball this in a different way than you eyeball it, and that's fine. Mathematically speaking, there in general will exist one line that fits the data better than any other line. can fit this data. That would be, of course, called a line of best fit. Those are the kinds of questions that we're going to start talking about next week, because really to find that line of best fit, particularly when I have a lot of data points, we're going to need to use some technology to really get into doing that. You don't want to do that part by hand. This week, though, we do want to do some of our analysis by hand. So what I want to do with my fit line, actually, is I want to choose a couple of points that it looks like my fit line did a good job of going through. So my particular fit line, this point right here, looks like I hit it on the nose. So that's this point for my data table, 1985, 430. And it looks like my fit line also did a good job of going through this point in the year 2010. So those 2 points from my original data table, the fit line that I sketched in here looks like it does a pretty good job of going through those 2 points. So let me take this opportunity to label the coordinates of those points. So this point was 1985, so that's x equals 5. And the y value was 430. And this point was the year 2010, so that was x equals 30. And in that year, the number of degrees awarded was 719,000. So there are my 2 points, 5, 430, and 30, 719. So for this week, our goal is going to be to get to the observation that all it takes to determine a line is 2 distinct points. This is often memorialized in the colloquial saying, the shortest distance between 2 points is a straight line. And in Euclidean geometry, that line is uniquely defined. There's only one straight line that passes through 2 given points in Euclidean geometry. And so that's the tack that we're going to take on it today. So what we want to do for the rest of our stream is figure out how to take those 2 points and determine an equation for a relationship between x and y whose graph will be the straight line passing through those 2 points. Right? That's now the main objective of the rest of the day today. Before we cross that bridge, let me take a quick 30-second pause and ask if you're watching live and have questions or anything you want to make sure that we hit in the second half of today's live stream. Contribute those into the Twitch chat or into the Slack channel right now. We're going to just take a quick 30-second pause rather, and we'll come back and take those next steps. All right, so we are going to go straight on ahead and tackle the formula questions of the day. And the way we're going to do that is by first developing a way of taking 2 given points in the Cartesian coordinate system, so 2 points on an XY coordinate graph, and finding an equation for the line that passes through those 2 points. This is a key, it's probably one of the most important skills that you learn in an algebra class in high school, or if you take an algebra class to catch up on your high school algebra in college. It's almost an undersold, undervalued skill, because this is the key way in which we get from data that we collect out in the real world to a formula that we can use the tools of mathematics to use as a predictive tool. So how are we going to do it? So there's 2 different, what we might think of as templates for a linear equation, an equation that describes a relationship between 2 quantities whose graph is a straight line. One of them is called the point-slope form of an equation. And the other is called slope-intercept. And I want to talk about them in that order today. Slope-intercept is the format that most students of algebra are the most familiar with. So this is the one that you'll probably remember when we talk about it. Point slope, on the other hand, is one that gets shortchanged, unfortunately, in a lot of algebra classrooms. But I happen to think that it's more valuable because it gives us a way to use the information that we have in the format in which we get it. And then we'll talk about how to convert a point-slope form of an equation into a slope-intercept form as well before we're done with today's stream. So that's where we're ultimately headed to. And I want to talk about where these equation forms come from. Why do they take the forms that they take? Like, why does it make sense that an equation whose graph is a straight line would have one of these two forms? Because it's in talking about this idea that we get to perhaps the most fundamental concept in all of equation modeling. And it's the word that's already on the screen twice. It's the word slope. One of the number one skills for us to get accustomed to in this phase of the course is how to think about a slope. Not just how to find a slope, but how to understand a slope. What does a slope actually mean? What is it telling us mathematically? And maybe more importantly, what is it telling somebody who's not currently sitting in mathematics class? How do you communicate an idea about a slope, a mathematical thought about a slope, to somebody who's not steeped in the mathematical discipline, who's not taking a college math course? What does slope mean to a layperson? Why should we care about what the slope of a relationship is? So I'm going to put a very heavy premium on that in our course, because it's that interpretive piece that really makes this stuff valuable. It makes it something that we can actually improve our lives and our communication and our success in our careers by having those tools. All right, so let's think about what is going to make this relationship tick. And the way that we do it is by labeling a third point on this line, and I'm going to give it the generic coordinates x comma y. Or maybe if you like, let's decorate these x's and y's with subscripts. x1, no, let's not do that. Let me avoid that. Let's just say x comma y. So x comma y is just some other point on this line. And it could be anywhere along this line. And so my goal is to figure out how is the x and y coordinate, how are the numbers in this ordered pair x, y related together based on the fact that they lie on the same line as the point 5, 430 and the point 30, 719. So to get there, we're going to use some basic geometry. And when I say basic, this is the kind of geometry that you probably spent some time talking about in high school and probably haven't had a chance to think about since then. That's okay. That's all in the game. But here's how it works. On my picture here, on my graph, I can connect those 3 points, the 2 points that I know and the third point that I don't know. I can connect them by just drawing in these two triangles, right? And these two triangles actually have all the same angles in them. I've got a right angle in my orange triangle here. I have a right angle in my blue triangle over here. Also, since these two lines, the two vertical lines, are parallel, the opposite interior angle theorem from geometry also tells me that the angles up here are the same as one another. And of course, the angle in this part of the triangle is the same as itself. So all of the angles in these triangles are the same. They correspond one to another. And so these two triangles are what we call in geometry similar triangles. And what that observation does is it tells me that these triangles have proportional sides. If one of them has a side which is twice as long as the other, then all of the sides are twice as long in one triangle as they are in the other. So that's the key observation that we need from high school geometry to get to where we're going. Okay, so now let's see what lengths of sides that we can determine in these triangles. It turns out that the orange triangle is the one that we have a much easier time figuring out the lengths of some sides. In particular, I can figure out the length of this horizontal side in my orange triangle just by observing that to get from this point to this point, I have to go from an x-coordinate of 5 rightward to an x-coordinate of 30. And what is the distance, the horizontal distance between 5 and 30? Well, that horizontal distance is going to be 30 minus 5. or 25. So this side of my triangle is going to have a length 25 because it's 30 minus 5. Let me attach a name to the quantity that we just computed. This quantity is often called the run. When we're computing the horizontal difference between 2 points in a Cartesian coordinate system. Horizontal difference. And the words horizontal and difference there I'm choosing very carefully. Horizontal indicates that this is a comparison of x values. Difference means that we're subtracting. So how do we compute a rise? We just subtract the x-coordinates of 2 points. Right? Just tells me how much horizontal distance, if you like, there is between the 2 points that we're looking at. The other side length that we can compute from the information we have is the length of this vertical side in my orange triangle. Right? This vertical side is going to be as much vertical difference as there is between the number 430, the y-coordinate 430, and the y-coordinate 719. How much vertical difference is there between those two observations? Well, I'm going to get that by, again, subtracting 719 minus 430. And that's going to give me, oh gosh, so 719 minus 430. Let me just do that calculation real quick. 289. So there's 289 difference between the vertical coordinates of these 2 points. That's a quantity that instead of calling a run, we end up calling a rise, because it's how much we're going up or down, right? It's a vertical difference. Again, we received this number by subtracting. That's why it's a difference. But it's a vertical difference because we're subtracting y's rather than subtracting x's. Vertical difference, right? So if I take out of this diagram, my diagram is going to get kind of busy here. Let me just extract what we need out of it. I have this triangle, and 2 of the side lengths on this triangle are now 25 and 289. Then I have the similar blue triangle, which is drawn around it. Let me make sure that this diagram is legible here. So the similar blue triangle that we draw around it that leads me up to my unknown point x comma y. Right? And the observation that these 2 triangles are similar is how we're going to figure out how x and y are related. So let's do that. In order to do that, we need to label the horizontal and vertical sides, the rise and the run, on the blue triangle as well. Now notice, the horizontal side of the blue triangle connects the point xy, the point whose x-coordinate is x, to the point whose x-coordinate is 5. So if I want to know what the run is on my blue triangle, just like we did on the orange triangle, we have to subtract the x values. We need the horizontal difference. Make some room here. And so the horizontal difference we're going to find by subtracting the x-coordinate of my second point, which is x, minus the x-coordinate of my first point, which is 5. So that's the rise in my bigger blue triangle. Right? For the same reason that the run, for the same reason that 25 was the run in the orange triangle, just by subtracting the x-coordinates. Same story for the y-coordinates. If I want to know what the rise is in my bigger triangle, I'm going to want, again, to subtract y-coordinates. The y-coordinate of the second point, subtract the y-coordinate of the first point. So instead of doing 719 minus 430 like we did here, I'm going to do y minus 430. And that's going to give me the rise, the length of the vertical side in this triangle. Y minus 430. Okay. So let's take stock. We have our two similar triangles. They're similar because they have all the same angles inside of them, and that means that they have proportionate sides. So the proportionate sides observation is exactly what we need to cross from graphical into formula. Because here's what proportionate sides means. It means that whatever ratio exists between the length of this blue side and its corresponding orange side, that same ratio also explains the relationship between the vertical blue side and the vertical orange side. So another way to say that is that it sets up a proportion. X minus 5 and y minus 430. The relationship of those two sides to the corresponding sides from the smaller triangle are that they stand in the same ratio as one another. So when I divide x minus 5 over 25, I divide y minus 430 over 289, I get the same proportion. And just by writing that down, we now have an equation that is going to constrain which x's and which y's are actually related by the relationship suggested in this data. It doesn't look anything like the equations that you're accustomed to for linear relationships. And that's fine right now. We're going to get there in the course of the next 15 minutes. But my hope is that this explains where these equations came from, right? That it really is nothing more than a proportion equation. So proportion equations are something we're also going to talk more about in the last part of our course because they relate to probability. But it's a proportion equation between the rises and the runs of two similar triangles that share the hypotenuses that all lie along this straight line. So this isn't quite the point-slope form of an equation yet. To get to the point-slope form, what I'm actually going to do is trade places. So I'm going to move this y proportion. I'm going to just flip-flop my equation left to right. I'm going to move the x stuff over here to the right. I'm going to move the y stuff over here to the left. No particular reason for that, other than that I want this to line up with what it looks like in your textbook. So all my y's on the left, all my x's on the right. And then to get this into the point-slope form that we're accustomed to seeing it, what I'm going to do is an algebraic move to this equation. What I want to do is I want to take this 289 that's sitting in the denominator, and I just want to move that 289 from the left side of the equation to the right. It's being divided, so the left-hand side of this expression right now is a division by 289. So to move that 289 to the right, I need to multiply by 289 on the left side of the equation and also on the right side of the equation. If I multiply by 289 on the left side, that multiplication is going to cancel out with the division by 289, which was the point, right? So those are going to cancel. And then after those cancel, we're going to be left on the left side of this equation with just y minus 430. Meanwhile, on the right side of this equation, I'm going to have 289 times the fraction x minus 5 over 25. Well, now I'm going to take and use the privilege of the commutative property of multiplication to take this multiplication that's happening here and take the denominator 25 and the denominator 1 that exists on the whole number 289, and I'm just going to trade their places. So flip-flop this 25 with this 1. When I do that, my new fraction that's sitting out in the front here is going to be 289 over 25, and then I'm going to have x minus 5 divided by 1. Okay. But if I divide by 1, I don't have to write division by 1 because it doesn't actually accomplish anything interesting. And what I have now is something that we are going to call the point-slope form of an equation for this line that we're looking at. So let me quickly erase it and rewrite it a little bit bigger just to make sure that it's as legible as possible in our video. So what did it look like? Y minus 430 was equal to 289 over 25 multiplied by the quantity x minus 5. There's what we call the point-slope form of an equation. So let's take a look at this equation and figure out where its various pieces will have come from. First of all, the y and the x, those are our variables. Those are our placeholders. Those are not going to go anywhere. Those have to be a part of our equation. Otherwise, they don't give us any place to plug in an x and a y to test whether or not a certain point is on this line. So that explains where the x and the y come from. The other numbers, 5 and 430, those two numbers, it's evident where they came from. Just looking back into my original picture, they were respectively the y-coordinate and the x-coordinate of one of the points on my line. So very often when you see this formula as a template in a textbook, 430 will be called something like y sub 1, and 5 will be called something like x sub 1. Really, those are just used to represent the coordinates of a known point that are on my line. And what's great about the point-slope form of a linear equation is that it doesn't matter which point we know. The point-slope equation that we write down is still going to be valid, regardless of which known point we write down, as long as the rest of the equation is indeed accurate. And then I have this fraction, 289 over 25. We can tell from this picture where the integers 289 and 25 came from. The 289 was my, let's call it the rise between my known points. Right? Rise between my known points. The 25 was the run between my known points. And if you like, you can think of that as the point-slope template. Right? Y minus the y-coordinate of a known point is equal to the ratio of the rise between two known points to the run between those same two known points, multiplied by the quantity x minus the x-coordinate of my known point. And that's all there is to it. Right? But of course, your textbook doesn't put it that way quite, because they take this number, this fraction, 289 over 25, that's sitting out in front of the quantity x minus 5 on the right-hand side. And in addition to thinking about what its individual pieces mean, the rise and the run, they also give the whole fraction a name. And that, of course, is called the slope of our equation. And very often, slope is represented by the letter m for reasons that I actually have no idea. M stands for slope, for I don't know why, probably in German or something, the word for slope starts with an M. So that is our definition of what a slope is. Our slope is the ratio of the rise to the run in any given linear relationship. Right? It gives us the language to talk about how changes, differences in one of my quantities are related to changes in the other. And so what I want to do right now is talk about how to interpret that particular slope. How would I communicate to somebody who's not sitting in a math class what the meaning of that slope actually is? Whoops. So what does a slope mean? How do we take the observation that we made over here in algebra land, that the slope of this is 289 over 25, and translate that over into a verbal description, a sentence that somebody might actually care about? Well, the key is to remember that the slope is a rise divided by a run. It is a vertical difference divided by a horizontal difference. If you like, maybe before we translate back to the verbal context, let's go back to our data table. So we were looking at these two data points, right? The year 1985, where 430 degrees were awarded, and the year 2010, where 719,000 degrees were awarded. My rise and my run, respectively, were the differences in the y values, so 289, and the differences in the x values, 25. So let's think for a moment about what those two numbers mean in the data table, and that will help us to get over to the verbal description. So what does 289 mean? Well, it's the comparison between the number of degrees awarded in 1985 and the number of degrees awarded in 2010. So I would say this as 289,000 more degrees were awarded when we compare those 2 years. What's the number 25 mean? Well, it's a measurement of the difference between the year 1985 and the year 2010. So 25 years worth of difference. 25 years ahead, if you like. Right? So over the 25-year period between 1985 and 2010, when I make that comparison, 289,000 more degrees were awarded 25 years later compared to 1985. So that's a context for each of those two pieces of my slope fraction, right? The rise and the run. So I could say that. Let me erase this observation here. I could say that by making reference to those two numbers. Over the 25 years, the number of degrees awarded increased by 289,000. But that is not usually how a slope gets reported, because that is still sort of keeping the rise and the run separate from one another, which is okay, but we get even more sort of power by thinking about the slope in its identity as a single number, a single rational number, a fraction, 289 divided by 25. So we'll go pull out a calculator and figure out what is 289 divided by 25. So the other nice thing about Desmos is that it is also a calculator. We do this division, it gives me this decimal, 11.56. Right? So if we want to, we can write 11.56 as the slope of my equation. And that's going to give me a different perspective on what this slope actually means. Let me find some space on the screen here. Maybe I'll erase this triangle. So on the one hand, our slope is 289 over 25. On the other hand, when I do that calculation, that number comes out to be 11.56. Or another way to think about what 11.56 is, if we think about it as a fraction, we can think of it as 11.56 over 1. Right? Anytime you want to make a fraction out of a number that's not a fraction, just make a 1 in the denominator and you'll be good. So why I like this interpretation is that this is now going to tell me, if we recontextualize, that we have rise on the top, which is a change in y values, numbers of degrees, and run on the bottom, which is a change in the year since 1980. Right? What this is now telling me is that this 11.56 can be thought of as 11.56 thousand more degrees, awarded, right? During what time period? Well, now my denominator, my run, is 1. So this means for each single year that passed. Right? If you're ever lost about how to contextualize a slope, one of the best things you can do for yourself is to write down the units of the numerator and the units of the denominator. So make it into a fraction, and then write down in the numerator and the denominator what are the units of your thing. Right? So this 11.56 is 11.56 thousand degrees awarded, and this 1 is a year. And now that I write that, Let me also put the word per here. Per is the word that we would use to represent that little fraction bar that's in between these. So now what I get is something that looks like a rate rather than as a ratio. 11.56 thousand degrees per year. And that's a rate of increase. So 11.56 thousand more degrees per year. And so if I wanted to get that number into the public consciousness here, that's how I would contextualize it. The number of degrees awarded increased over this time period at a rate of. If you're using the words at a rate of, that means you're probably thinking and communicating correctly about a slope. At a rate of 11.56 thousand additional degrees per year. So words like additional and more are also especially important in this communication. Right? And that is probably the most conventional way of contextualizing a slope. Give me a single number rather than thinking of the numerator and denominator of our fractions separately, and then use that number to say this is the rate of change of the y-coordinate, the vertical coordinate, per a change of 1 unit in the x-coordinate, in the horizontal direction. Per every 1 year that elapses, we are adding 11.56 thousand additional associates degrees, if my slope is 11.56. So that's both sort of a description of how the point-slope form of an equation works, and also it's a description for how to contextualize the slope. How do we tell a story about what the number that's sitting in front of that parentheses x minus 5 actually means about the context of the situation that we started with. So let's wrap up our stream today by taking our last step, which is to turn this rather complicated looking equation describing the relationship between year and number of degrees awarded, and turn it into a slightly more sterilized format, a format that's actually a little bit easier to use to make predictions, and we'll finish up by actually making the prediction that we set out to make here. How many degrees in 2020 according to the model that we've developed here. So to figure that out, in a slope-intercept equation, what we want to do is we want to get one of our variables, and the convention is usually it's y, we want to get one of our variables by itself on one side of the equation. And the reason that's helpful is that if you supply for me a value for x, then the only place x is going to show up is on the right side of this equation. The only place y shows up is on the left side. And so I can use this equation just by doing arithmetic on the right side to figure out for a given value of x, which y. If you tell me the year, I can use just arithmetic and not algebra to then determine how many associate's degrees were awarded in that year. And that's ultimately what we want to do to make our prediction. So how do we get from point slope to slope intercept? Well, let me take the luxury of putting 11.56 in my slope now, just so that we don't have to cart that fraction around anymore. And figure out how we get the y by itself. Well, y is almost already by itself on the left side of this equation, right? All we need to do, the only thing separating it from loneliness, is this 430, which is currently being subtracted from the y. So, as is customary with algebra, we get rid of an operation by applying the opposite operation. Add 430 to get rid of the subtraction. And I have to do that on both sides of my equation. So after I've done that, my right side is now 11.56 times the quantity x minus 5 plus 430. So now my y is by itself. But it's maybe not the simplest way that I could express this particular mathematical thought. Let's simplify the algebra that's on the right side of this equation. We can do that by distributing the multiplication, 11.56 times x minus 5, distributing that across the subtraction inside the parentheses. If I do that, I'll get 11.56x minus 11.56 times 5. And 11.56 times 5, let's pull out my calculator here, is 57.8. And then my last step is to combine the like terms. Minus 57.8 plus 430, I get 487.8. Wait, not quite. Hold on. 372.2, sorry. 372.2. Okay. And now we have completely simplified the expression on the right-hand side of this equation. And we've arrived at a form that is often called the slope-intercept form of an equation for a linear model. So let's take a look at the main features of a slope-intercept form of an equation. The first thing we notice, 372.2, first thing we notice is that our 11.56 is still there. It's still present, right? That same number which was identified as our slope in the point slope format still shows up in my slope-intercept format, right? So evidently, the coefficient of x in the slope-intercept equation is also known as the slope. So call it m, right? M is the slope of our linear relationship. But we do have a new number showing up, 372.2. Let's see if we can figure out what interpretation that 372.2 has in the context of our data and our numerical and graphical representations of this problem. So let's uncover our graph again. And draw my straight line through these points the way that we did previously. Okay, so there was my straight line, of which this now is an equation. And what is 372.2 actually going to mean? Well, the answer to that question can be found by answering a different question. And the different question is, how could I get the number 372.2 by itself in this equation? Well, the way I could do it is by substituting the value 0 for x. If I put if I put 0 in the x space here, then whatever my slope is, multiplying it by 0 is going to make this term of the expression go away. And it's going to leave me with y equals 372.2. So the first thing we notice about that number, 372.2, is that it's a value for y, right? Which, in the context of our problem, means it's a number of degrees awarded in thousands. So 372.2 is a number of degrees. 372.2 thousand degrees awarded. I'll write that in the verbal description over here. But the question is, when? When were 372.2 thousand degrees awarded? Well, in order to get that value of y, we had to substitute 0 for the value of x. So I could just write over here, when x was equal to 0. But that's not a very good verbal communication, because the verbal communication should tell me what x means and what 0 means. Well, going back again to the context, x in this graph is the number of years since 1980. So if x is equal to 0, that must mean that was 0 years since 1980. Right? So that gives me some context and interpretation for the number 372.2. It's the value of y when x is equal to 0. And on a graph, it's called the y-intercept. It's called the y-intercept because it's where this graph ends up on the y-axis when the value on the x-axis is 0. So it gives me the coordinates of the point at which this line crosses the x-axis. There's my 372.2. So my slope-intercept equation has on one side of the equation just the variable y. On the other side of the equation, it has the expression m times x plus b, where m has the interpretation of the slope, the ratio of rise to run, And B has the interpretation of the y-intercept. It's the value of y when the value of x is 0. In this case, when the value of x is 0, that means that we were talking about exactly the year 1980. And so here is a verbal rendition of everything we've gotten so far out of this equation model. Y equals 11.56x plus 372.2. And so to wrap up our stream, we want to finally answer the question, where does this model put us in the year 2020? So to figure that out, all we have to do is substitute the value 40 for our value of x, and then make the evaluation. So in 2020, x is equal to 40, and so y is equal to 11.56 times 40 plus 372.2. We'll do out that arithmetic by multiplying first, 11.56 times 40. That gives me 462.4. I add 372.2, and I get 834.6. 834.6 is the y-coordinate when the x-coordinate is 40. And so we predict in 2020, 834.6 thousand degrees awarded. And that closes the loop on the prediction that we wanted to make. So look back one more time at the structure of the problem that we've just solved. The problem started out as a problem with a data table. We took the data in that table and created a visual representation in a graph by graphing the ordered pairs. Then we computed the slope. So we sketched in by eye a fit line, took 2 points on that fit line, and used those 2 points to determine my slope. The rise, the difference in their y-coordinates, divided by the run, the difference in their x-coordinates. That gave me this fraction 289 over 25, or 11.56. We interpret that 11.56 as the rate of increase in the number of degrees per year. Then we can use the point slope form of our equation to write out a relationship between x and y. Y minus the y-coordinate of one of our known points equals the slope times the quantity x minus the x-coordinate of my known point. That gets me the hardest step. It gets me the step into formula land. Then by simplifying that formula and getting the y by itself, we discover that there's a slope-intercept format, a y equals mx plus b, in which we can contextualize the intercept by saying this is how many degrees were awarded when x was 0, in other words, in the year 1980. So the most important skills here to get comfortable with are translating between the numerical and the graphical. So being able to graph a set of data points, and then sketch in, by eyeball and by hand, a fit line. Then, taking 2 points on that graph, find an equation for the line that goes through those points, for which the first step is finding the slope. That is the most important first step in the process. Don't even think about y equals mx plus b until you've computed the slope m first. Once you've done that, then the point slope form of an equation can get you there. You can simplify it if you want to, and be able to communicate about what the slope tells me and what the intercept tells me. Not me as a math professor and a mathematician, but me as somebody reading a professional article, or me as somebody reading the Boston Globe, or me as your boss reading an annual report, right? Think of those audiences. Those are the audiences that you're going to need to communicate mathematical thoughts to in your world. Once you're done with your math classes in college, you're probably not going to have other math professors that you need to communicate with. So ultimately, I want you to be able to communicate with other people in the world, not just me, about mathematical thoughts. So the more practice that you get with this, the more that it will start to become a new habit of thinking for you. And even though it took us an hour and 15 minutes really today to talk through all of the different facets of this one problem, I think that this is kind of what we need to do in the beginning so that we get comfortable with all the different translations and the ways that we talk about these mathematical ideas, especially how do we talk about them using words. So we'll push this a little further next week when we use technology not just to find a fit line for a set of data, but to find the best fit line for a set of data. So we're going to continue thinking about linear models next week, but using technology to come up with the best linear model that we can. I look forward to doing that with you, both using our Desmos online free tool and also using Microsoft Excel when we come back to this topic next week. I'll see you then.